Today, we are diving into one of the most elegant ideas in all of geometry, the tangent. It's a concept that's all about a single perfect point of contact. And as you're about to see, that one simple idea unlocks some surprisingly powerful rules. So here's our game plan. We'll start with the basics, the different ways a line and a circle can even interact. Then we'll zero in on that special moment of contact. From there, we'll uncover a couple of fundamental theorems and see how they help us solve some pretty tricky geometry problems. Let's kick things off with a super simple question that really sets the stage for everything else. What happens when a straight line meets a perfect circle? It sounds basic, I know, but there are really only 3 ways this whole encounter can play out. All right, section 1, a circle meets a line. Let's explore those 3 possibilities. Okay, first up, the most straightforward case. The line and the circle just completely miss each other. They don't share any points, they just exist on the same plane, doing their own thing. We call this a non-intersecting line. Simple enough, right? In our second scenario, the line doesn't miss, nope, it slices right through the circle. And when it does that, it crosses the circle at 2 separate distinct points. This kind of line has a special name. We call it a secant. And that brings us to our third and, honestly, the most fascinating possibility. The line doesn't miss and it doesn't slice through. Instead, it just grazes the edge. It kisses the circle at one and only one perfect point. And that, my friends, is a tangent line. You know, this unique moment of contact is really what it's all about. So let's zoom in a little and define exactly what makes a tangent so special. That single, common point has a name, of course. It's called the point of contact, or sometimes you'll hear it called the point of tangency. This is the entire foundation of the relationship. Everything important happens right at this spot. Now, here's a really cool way to think about it. Picture that secant line from before, the one that cut through the circle at 2 points. Got it? Okay, now imagine sliding that line away from the center. See how those 2 intersection points start getting closer and closer until, bam, they merge into one single point. In that exact instant, your secant has transformed into a tangent. And this isn't just some abstract math concept. You see tangents everywhere. I mean, think of a bicycle wheel rolling along the pavement. The ground is a perfect tangent line to the wheel, and at any given moment, there's just one tiny point of contact. Or picture a rope pulled super tight around a pulley. Those straight sections of the rope are tangent to the circular pulley. All right, now that we've got a good handle on what a tangent is, it's time to uncover its first secret power. There's a hidden geometric rule here that is always, and I mean always, true. And here it is, Theorem 10.1. It says that if you draw a line from the center of the circle out to that point of contact, which is just the radius, right? That radius will always meet the tangent line at a perfect 90-degree angle. They're perpendicular every single time. So how can we be so sure this is true? Well, the logic is actually pretty slick. Just pick any other point on that tangent line. Because the line only touches the circle at our one special point of contact, this new point has to be outside the circle. And that means its distance from the center is longer than the radius. So the radius is the shortest possible line you can draw from the center to the tangent. And in geometry, the shortest distance from a point to a line is always the one that forms a perfect right angle. Okay, we've got our first rule in the bag. Now, let's tackle a new question. If you pick a point just anywhere on the page, how many tangents can you actually draw from it to a circle? Well, it turns out the answer depends entirely on where that point is located. It all boils down to 3 really simple cases. If your point is inside the circle, well, you can't draw any tangents. 0. Any line you draw will just be a secant. If your point is on the circle, you get exactly 1. And if your point is outside the circle, you can always draw exactly 2 tangents. Now, this brings us to our second powerhouse theorem. When you draw those 2 tangents from a point outside the circle, something really remarkable happens. The length of the tangent from that external point to the point of contact is exactly the same for both lines. They are always equal. So why are they equal? The proof for this is just so elegant. If you connect the center of the circle to your external point and then to the 2 points of contact, what you've done is create 2 right-angled triangles. Now, these triangles share a side, the hypotenuse, and their other sides are both radii, which means they're the same length. So the 2 triangles are perfect mirror images of each other. And if the triangles are identical, it means their final sides, the tangent segments, must also be equal in length. So these theorems aren't just neat little facts to memorize. They're actually incredibly powerful tools for solving problems. Just check out what this stuff can do. If you have two circles with the same center, a chord of the larger circle that's tangent to the smaller one is always perfectly cut in half at the point of contact. And even cooler, if you draw a four-sided shape, a quadrilateral, around a circle so that all four sides are tangent, the sums of the opposite sides will always be equal. That's a direct result of our equal tangents rule. You see, when it comes right down to it, it all comes back to two powerful rules that unlock a huge range of geometric puzzles: the right angle rule and the equal lengths rule. So let's do a quick recap of the big takeaways. Number one, a tangent is a line that makes a single, perfect connection with a circle. Number two, that connection always forms a right angle with the radius. And number three, when you draw two tangents from the same outside point, they are always identical in length. So that's the geometry of the tangent. But it leaves us with a bigger question, doesn't it? This whole idea of a perfect singular connection is so fundamental. Where else in the universe do we see it? In physics, or art, or maybe even in nature? Definitely something to think about. Thanks for watching.